Thank you very much, Brim, for the introduction. Also, thanks to the organizers for the invitation to the conference. The first thing I should say is that this is a joint work with Julien, Leroy, my supervisor at the University of Liège, and Pierre Stas, a PhD there. And they are the only people from Belgium who are not here. Okay, so the topic is dynamics of Dendric subshift. This is a topic mostly in symbolic dynamics. I'm going to introduce this class, why it is relevant to study. I'm going to focus on one of the results we have, which is around the substitutive structure that we have described for them. Okay, so I'm going to introduce the language. I have just this slide. The universe for me, I'm going to use the language of symbolic dynamics. So the universe here is the full chip, A to the Z. It consists of two-sided infinite words. We are going to use substitutions. So for me, substitutions are monoid morphisms between these monoids of words. It's important to say that they are non-erasing. So the image of every letter is not the empty word. And finally, the objects that we want to study are subjects. So these are sets of biinfinite words that are closed and shift invariant. It's important to say that although I am talking about subjects, all the things I will say also works for single infinite words. So use the language that you find the most convenient. We're going to use a lot the language of the subject L of X, which is the set of words occurring in any point in the subject, finite words. And the last important remark here is that we are only going to consider minimal subjects or uniformly recurrent subjects. These are synonyms. This is mostly for simplicity because we want to keep a simple presentation without technical details. Okay. So dendricity is motivated by the study of the complexity function. So the complexity function counts the different number of words of a given length in the subject. It is a very old invariant. It's a conjugacy, more precisely, the growth of it is a conjugacy invariant. So we can use it as a classification tool, and it's one of the simplest and most useful classification tools that we have to study subjects. At the same time, it is very coarse. It doesn't say much about the subject. That's why, especially in the low complexity case, we have other tools such as the Rauzy graphs. Now, I'm not going to use Rauzy graphs, but they're important to motivate dendricity. So the thing about Rauzy graphs is that we have one of them for every length n. And they are built in the following way. So they are directed label graphs. The vertices correspond to the set of words of a given length n, and transitions are given by words length n plus 1 in the subject. So they are, in some sense, using, of course, these overlaps. So they are, in some sense, like a finite static photo of the subject. Using them, we can say a lot of things in the low complexity case. If we study the combinatorial properties, what kind of vertices it have, the way they evolve is also important. And it has been an important tool for proving classical theorems, such as Boucher-Vinsa's theorem on the number of periodic measures. Now, a more recent version, a newly introduced version of the Rauzy graphs is given by extension graphs. These provide a different view of the evolution of Rauzy graphs, and this is what we're going to use. So, yes, the formal definition is here, but I want to focus on an example. So the first thing I should say is that, we have a subject, this is the context, and we have one extension graph for every finite word in the language. So they are no longer indexed by length. And the graph is now, this time, undirected and unlabeled. It consists of a bipartition in which we have one copy of the alphabet on the left side and one copy of the alphabet on the right side. And the vertices are given by this rule. So we have all pairs in the on the left and right copy, respectively, A, B, such that they define a bi-extension of the word that we're considering. So A, U, B. So it encodes all bi-extensions of the word. And as an example, I have this. This is a point X, a uniformly recurrent point X in a subshift X, which is minimal. We have three letters, so we have this left copy and right copy. And for instance, we have here the extension graph of the empty word. This is something that we can also consider. And the fact that we have in this extension graph the arrow AC means that the word A concatenated with epsilon concatenated with C occurs in the language. And this is something that we see. For instance, here AC occurs. On the other hand, we have, for instance, the extension graph of the letter C, a word in the language. And the fact that, for instance, AB is in the extension graph is reflected by the fact that the word ACB occurs ACB here in the language. Okay, so we have this different view of the extension graph. They represent some information about Rauzy graphs. But why is interesting to consider them? And I want to focus a lot on trying to convince you that this is an interesting point of view and an interesting way of encoding data. I want to focus on two examples. The first one is this old theorem by Tiedemann. I'm going to present a different version, a more modern version due to Mélodie Andrieux and Julien from 2022. And it says the following. So here we have a subshift, x, we have mu, an ergodic measure, and then we consider the letter frequency vector, this one. We assume that it has rationally independent coordinates, and then we have two important conclusions. The first one is that we have a lower bound on the complexity function, this one. And more interestingly to us, we have that if this lower bound is attained for every n, then every extension graph in the subshift is a tree. So we have here some conclusion about graph theoretic properties of the extension graph based on these two elements, rationally independent relative frequencies and complexity function. We're going to see that these kind of restrictions on the extension graph impose a lot of rigidity on the system. They impose, for instance, well, we're going to see it really imposes several things. And also, this is a natural situation for several kind of researchers, right? This is something that occurs naturally when studying equidistribution of sequences, for instance. Okay, and a more general situation than this is a bit abstract, but this is a much more general situation in which we can encode things using extension graph is this one. So what do we have here? The idea is that we have a geometric system given by Z and the action T, and then we are going to define a symbolic coding, and we're going to say something about the symbolic coding. So here in this case, Z is a compact meteorological space, and it is geometric in the sense that it is a connected space. Then we have T, the dynamics. In this case, it is enough to have a bijection. And then we have a topological partition to define the symbolic coding. So I am not defining this. The thing is that we don't want anything too crazy. So for instance, if we have a partition using Rauzy fractal, this is fine. But we don't want something really crazy. What's important here is that these atoms of the partitions, which are indexed by a finite alphabet, are also connected. So we have this really strong geometricity feeling here. And also we want some continuity properties, of course, on T. With this, we can define a symbolic coding, which is the set of bind-field words that define an itinerary of some point Z in the geometric space. And the conclusion is that here, all the extension graphs are connected. And as I was saying, we're going to see that this is something that imposes a lot of rigidity on the subject. Concrete examples, integral extension transformations. They are covered by this theorem, and moreover, in this case, in the minimal case, the extension graphs are trees, so connected and acyclic, much stronger. We also have Arnoux-Rauzy subshifts because they can be defined as codings of Rauzy fractals. And in a different direction, we have hypercubic billiard words. And these are also codification of some kind of flow on a hypercube in a d-dimensional hypercube. And in this case, we don't have trees. We only have connected extension graphs. So these two different natural situations in which we have these conditions on extension graphs. Yeah. Yeah, sorry. So here I'm talking about the natural coding of interval exchanges, and here the coding of the exchange of pieces of the Rauzy fractal. Okay, so before continuing, I need some definitions. So a subshift X is said to have a connected language if every extension graph is connected. And more importantly, we have that it is dendric if all these extension graphs are trees, so connected and acyclic. And finally, it's also important to consider eventual dendricity. Here, what we want is that extension graphs are trees, but we admit finitely many extensions. Equivalently, we can say that a subshift is eventually dendric if the extension graph of every long enough word is a tree. And to give a feeling about the relationship between these concepts, we have this proposition by Bakova and her co-authors, in which we have the following. So we have a minimal subshift X with a connected language, and we have three important conditions. The first one is the lower bound that we saw in Tiedemann's theorem. This is not a coincidence, of course. And then we have dendricity characterized in these terms. So X is dendric if and only if we attain the lower bound. And then we have eventual dendricity occurs exactly when we have linear complexity. So this is an instance of something more general. Dendricity is going to be this very good property from a combinatorics on words point of view, because here we have this very exact quantity. We're counting things very nicely. On the other hand, eventual dendricity is going to be more natural from a dynamical perspective. It's going to be the closure, the dynamical closure of dendricity. That's why we have something more qualitative. Okay, and to talk about the kind of rigidity that we can observe in dendritic subshifts, I need to talk about return words. So if I understood correctly, most people here are already aware of these things. That's why I'm going to use mostly a figure to describe it. So let's say that we have a point X in a uniformly recurrent subshift, and we have a set of words, all of the same length. Let's say here we have 2 words. To compute return words, what we do is that we mark all occurrences of these words, the red word and the blue word, like this. And then what we see between consecutive cuts is called a return word. More importantly to us, what we can do with return words is to define a coding. So what we do is that we consider a symbol, a new symbol, capital letters in this case, to encode the fact, to encode every written word. In this case, we have only 2, AB, ACC, and BCA. This time, we need something more. The symbol is equipped with additional information, the word of length 2 that we see after the end of the written word. So for instance, AB encodes the fact that we have this written word and then AB. For instance, here we have the same capital letter, but BC is different because we see a different word of length 2 after this. With this, we get a new infinite word, the word Y, and the set of all words Y that occur in this way, when we start from the point X in the subshift X, produces a new subshift, which is what we call the coding subshift. And we also have a substitution, which is this one, the one that replaces the capital letter by the return word that we are encoding. Okay, and this is one of the important constructions of the representation, coding subshifts given by return words to some set of words. Okay, the last thing is that we're going to work a bit on the free group. And that's why we consider the monoid of words A star to be a subset of the free group in the natural way. Then we can also extend substitutions, which for me are morphisms, to the at the level of free groups in the natural way. There is a unique way of doing this. And with this, we can state one of the theorems. It is a characterization. It was proved in 2 parts, in one paper by Valérie Berthet, co-authors, and Francis Gerard and the co-authors. It says that a minimal subshift is Dendric if and only for every word W, if we consider the return words to the singleton W, then what we get is that the extension of this morphism to the free groups is an isomorphism. So just to recall, in this context, we have that this thing is an isomorphism if and only it is both onto and the sizes of the generators are the same. I want to stress on the fact that it's a very strong condition because even finding and constructing subshifts in which all written words have the same cardinality, which is implied by this condition, is something difficult. And it was one of the motivations of defining this class of dendricity. One of the results that I can show you here is that we have a generalization of this kind of a result for the connected language case. So, for instance, here we have that a minimal subshift has a connected language. If and only if we have something similar, but with 2 important differences. The first one is that the construction here is a bit different. What we do is that we take a word U, and we consider the coding given by U. And then we consider a word U prime in the coding, and here is where we consider return words. Here we consider the return morphism in the coding. And what we want now is that this morphism is onto. So 2 important differences. We iterate the construction in this abstract way, and we only require it to be onto. Okay, these kind of results are very qualitative, but they already have some consequences. So for instance, as a corollary, we have the following. A minimal subshift with an eventual connected language is eventually dendric if and only if it has finite topological rank. And this has consequences, for instance, when we study, let's say, hypercubic billiard words. So as a consequence of this, hypercubic billiard words, they don't have linear complexity. This is something very well known. And as a consequence, a hypercubic billiard word cannot be generated, for instance, by a unimodular directive sequence. So this is something that means something for some experts. Okay, and there are many other things that we know about this class. For instance, eventually dendric subshift can always, a subshift like this can always be reduced to a dendric subshift using a Kakutani equivalence. This is something defining dynamical terms. I was saying that this is, in some sense, the dynamical closure of dendricity. We also have that dendricity is preserved under some number of operations. So for instance, maximal bytex decoding. On the other hand, we have that eventual dendricity is preserved by dynamical version of these things, K-to-1 extensions, dynamical conjugacy, and dynamical factors. We have descriptions of the dimension group and bounds for the number of different ergodic measures that can occur here. And I forgot to say this, but Dendric subshifts also include many classes of systems. So for instance, Sturman subshifts, Arnoux-Rauzy subshifts, interlexing transformations, etc. At the same time that they maintain core properties, the ones described here, for instance. So we have a huge type of, not huge, but we have a large variety of dynamical behaviors. IETs are in general weakly mixing. On the other hand, these are in general of discrete spectrum. So many different things. Our work was to continue exploring the dynamical properties that we can observe in this class. And as I was saying, we're going to focus today in the S-adic structure. Now, to describe the substitutive structure, this is a bit technical, so I'm going to mostly introduce this using an example. The example is the Sturman example that was presented by Pierre yesterday. So we have here a Sturman example like this. This is a Sturman sequence. And what we can do is that we can codify it in a particular way. So this time we're going to use this particular morphism. This is a very well-chosen morphism. And what we do is this. So the important property here is that every one in this sequence is followed by a zero. So we can group these occurrences of 1 zeros in this way. We get these red boxes, and we can obtain a new sequence in this way. This new sequence defines, again, a Sturman sequence. This is the really amazing thing about this example. So since it defines, again, a Sturman sequence, we can iterate the procedure, possibly with a different substitution. In this case, it is the same. But in the third step, we get a different substitution, theta 0. In general, we only need 2 different substitutions. If we stop after a number of steps, what we have is that we can recover the original substitution just from the letter that we have here and the substitutions that we got. It's important to remember the order in which we get the substitutions. So we can simplify the substitution rules like this. Okay, now I'm going to give the formal definitions, but I want you to remember mostly this figure when we talk about derivative sequences and substitutive structure, this tree-like structure. Okay, so the main object here for defining a substitutive structure is the notion of derivative sequence. And a derivative sequence is simply a sequence of substitutions like this, a countable sequence of substitution, having this particular form. What's the idea? The domains and codomains of the substitutions are coherent in some way so that we can consider the composition of them in the reverse order. With this, we can form base blocks which have this form, so we consider the first n substitutions, their composition, and then we apply the resulting substitution to a single letter. This is called a base block. And with this, we can define a subshift in a, let's say, intuitive way by saying that the subshift generated by the derivative sequence is simply the set of limits of base blocks. More formally, what we have is that this is the set of all bi-infinite words, such that every finite subword occurs in some base block. The idea, in any case, is to take limits of these base blocks. But this is more abstract. That's why I want you to remember this figure. Okay. Now, what's the deal about a substitutive structure? Why should we try to find such a structure for dendritic subshifts? So I'm going to explain this. I'm going to start with a fact. The fact says that every transitive subshift is generated by a derivative sequence that uses only finitely many different substitutions. Moreover, every subshift is generated by some derivative sequence. So in general, any symbolic system is generated by a derivative sequence. The thing is that in general, what we want is to have a good S-adic representation, a good derivative sequence generating the subshift that we want to study in such a way that the combinatorial properties of the derivative sequence encode in some way, an efficient way, the dynamical properties that define the subshift. And this is something that has been known for several classes of subshifts. So for instance, Sturman subshift, this is the example that I presented before. Automatic sequences using constant length substitutions. Minimal subshift, this is the work that was studied in terms of Bradley-Bershik diagrams, Giordano, Bunman, and Scott. Also for linear and non-superlinear growth complexity subshift, this was done in my PhD thesis, doublet subshifts, and so on. Many examples. And once we have this derivative sequence, the thing is that there are many techniques to exploit the structure and obtain interesting information from the sequence. That's why, yes, So the S-adic framework has permitted the unification of a variety of results and techniques. And in order to access to the S-adic toolset, it's necessary to first translate these properties that define the system into a directive sequence. So the problem here is to find an S-adic description for the class of Dendric subjects. Yes, okay, so what kind of a description we should try to find? The thing is that there are some hints, because we know that there are two important subclasses of Dendric subject. The first one is the class of Sturman subject, and for this one, we already have a good description, which is given by these two morphisms, theta 0 and theta 1 that we used before. In this case, the description is very simple. We can put them in almost any order. The only restriction here is that we need to be sure that the subject that we generate is minimal. In this case, this is equivalent to stating this property of primitiveness, which I'm not going to define, but it's very simple combinatorial condition. Now, for the class of codings of IETs, we only have an S-adic structure. And this, in this case, this comes from Rauzy classes, the things that encode the Rauzy induction. So in this case, what we have is that we have these Rauzy classes, graphs, in which we can add as labels to the directed graphs, in which we can use elementary substitutions as labels. And IETs, the codings of IETs, are precisely those subshifts that are generated by directed sequences that we can read from an infinite path in this graph. So in both cases, we have some kind of very finite automaton generating everything. That's why the natural question here is whether we can find an S-adic graph description for Dendric subject. And this is what we got. But before, we have a previous theorem on this direction. This is due to Julien Leroy and his former student, France. And what they got is the following. So for every V, which represents in this case the size of the alphabet that we're considering, we can find a directive label graph GD satisfying three properties. The first one is the most important. Any minimal subshift in this particular alphabet is Dendric, if and only if we can find a path this in this graph that has as labels these morphisms that define in turn a directive sequence, and this directive sequence generates X. So this is the same kind of characterization that we have for Sturmians or for IETs. The thing here is that although this graph has a finite vertex set, it has infinitely many edges. And moreover, the labels that we need to use here is what they call Dendric return substitutions, of which we don't know much. It's very difficult to describe. So in particular, we don't have a concrete description of Dendric return substitution, and in general, we have infinitely many of them. So in this particular graph, it is difficult to describe, but they have the vertices? Yeah. No, they are graphs themselves. They encode evolution of some graphs similar to Rauzy graphs. Okay, so as a conclusion, we have that the transfer of dynamical data into combinatorial data is not complete because we don't understand these two parts. So what we wanted to do with Julien was to improve this part. Okay. Yeah, as I was saying, so and the basic approach to try to solve this problem is based on a theorem by Valéry, in which they prove that these Dendric return substitutions are always composition of elementary substitutions. These elementary substitutions are defined like this. The important thing is that we have finitely many of them. So they're defined for two different letters, A and B, and we have one of prefix type and one of suffix type. So in general, we have finitely many of them. Yes, and so our approach was to use elementary substitutions to try to understand this part. So I'm going to present first the theorem, and then I'm going to give some comments. So this is what we got. It's very similar to what we had before, but there are some important differences. So again, we have for any alphabet a directed graph, directed label graph GD, in which we have that any minimal subshift that is a minimal subshift is eventually Dendric. This is the first difference. Now we're characterizing eventual Dendricity. So a subshift is eventually Dendric if and only if we can find this path in the graph, and now an arbitrary substitution sigma, an arbitrary substitution defined on this alphabet, such that this directed sequence in which we have this arbitrary substitution at the beginning, and then the path that we read from the graph generates X. Two technical conditions, these are really not important, but we need to put them there. Now, the characterization is a bit different because now we're considering here the dynamical closure. And moreover, we have now a finite edge set and also elementary morphisms as labels. So now we have finitely many substitutions. Okay, so we have solved the problems, and we have, in fact, something more. So for instance, we have that this graph simulates other inductions and renormalization processes. To be more precise, in this graph, we can find a subgraph which corresponds exactly to the Rauzy classes that describe Rauzy induction for either electron transformations. This also uses elementary morphisms. And we also see that Arnoux-Rauzy substitutions are determined by loops in the graph. And we can also simulate Cassegn's multidimensional continuous fraction algorithms, because this also is defined by a subgraph in the graph. Sorry. And I don't have the time to talk about all the technical details, but I'm going to skip to the last part to give the final comments. So two things. The first one is that we have a similar structure here for the case of connected languages. But this is more difficult to describe because, in particular, in this case, we cannot use a fixed alphabet. In this case, we have a fixed alphabet. So, in particular, in this sequence that we have here, for instance, if we shift the directly sequence, we get a new Dendric subtype. So, it is a renormalization process in which, from one Dendric subtype, we get another one. In the case of connected languages, it is not possible to do something like this over a fixed alphabet. This is something we can prove, and this, let's say, formal mathematical theorem. And the second comment is that we would like to use this theorem to get some applications. So, for instance, I mentioned one of the theorem before, a theorem by Darnam and Fickenshire, in which they obtain a bound for the number of ergodic measures. We know that this is not optimal. We would like to use the information given by the vertices here to obtain a finer bound for the ergodic measures, or maybe to get a formula based on the path that we read. Also, we would like to apply this to design multidimensional continuous fraction algorithms, because we know that Cassegn's algorithm is very efficient from a variety of point of views, but it only works in dimension 3. We don't know how to generalize it. So one possible application would be to try to do the same thing, but for higher dimensions. And also, there is another question related to realization problems. So as I said before, if we start from a geometric system, this connected situation, the code is going to have a connected language. What about the converse? If we start with something that is Dendric or it has a connected language, can we find a geometric system from which the subject comes from? It would be really nice to have something like this, but it seems very difficult as well. I'm going to stop here. Thank you very much for your attention.